The next topic in chapter 3 is 3.2, and it's simply titled torque. And as we work with electrical machines, we realize that electrical machines, for the most part, they rotate. So when we need to understand this turning force, we need to understand what torque is. Now, on page 51, he gives us a little background on that. So let me bring up the slide here and we'll look at this together. We've got this going on and here. Okay, so as you're looking at figure 3.1, this represents exactly what torque is. Torque is produced when a force exerts a twisting action on something, he calls them a body, tending to make it rotate. And torque is equal to the product of the force times the perpendicular distance between the axis of rotation and the point of application of the force. Okay, so the point of application that we're talking about is right here, okay, in the slide. We're talking about right here. That's the point of application. And then, you know, this is the distance, the radius and the distance to that point of application. So he gives us an example. Suppose a string is wrapped around a pulley. It has a radius R. If we pull the string with a certain force, the pulley will tend to rotate. The torque exerted on the pulley by the tangential force is given by our next equation. And let's see if I can write here on this. Yeah, let me go to a different screen and we'll do some calculations based on this diagram. So let me stop this share and go to a different share. And let's see here. We'll go to OneNote. Bear with me here, sports fans. We'll get there. All right, so we want to share the pad, share here, and work some problems. Because I'm working to make this seamless, but in the meantime, we'll just kind of get through my sort of moving from one device to the next. But hopefully, eventually, this will get a little smoother, and we'll miss these periods of me transitioning from one to the other. But equation 3.2, all right, 3.2 is that torque is equal to this force exerted times the radius from the point of where the force is exerted. Okay, he says a motor develops a starting torque. So torque, we want to get used to these terms. When we're talking about electrical machines and motors, particularly we want to get used to these terms like torque so that we'll understand them. Even if we're electrical spark heads, as they call us, we want to understand what torque is. And he says torque given is 150 Newton meters. If the pulley on the shaft has a radius, wait a minute, he's messing with us. He says not a radius, a diameter. Okay, no problem. He says the diameter is equal to 1 meter. Calculate the braking force needed to prevent the motor from turning. Well, that's phrasing something differently. And you know, the force that you need to keep it from turning is the same force that is generated when it is turning. Okay, but anyway, first thing, we have an equation, but it says nothing about diameter. It is given in terms of radius. So what we want to do, right? What we want to do to get to the radius, we just want to divide that by 2, right? Which is the radius, and it would be 0.5 meters is the radius. So if we go back to our equation, and again, we're wanting to know what is the force I would have to apply to get this amount of torque. All right, so take our equation, let's plug in what we know. I've got 150 Newton meters is the torque. The force is what we're trying to find out, and the radius is 0.5 meters. Solving that for F, I'm going to get 150. I'm going to drop the units for to make this go a little faster, and I'm going to divide that by 0.5. And so what that tells me is that 150 divided by 0.5 gives me 300 newtons, which is our measure of force. So if I apply a braking force of 300 newtons, that would keep that from rotating. It's just, saying the same thing from a different perspective. Or if I just wanted to think, well, what is the torque if I apply a force of 300 newtons to a radius of 0.5 meters? I get 150 Newton meters. So it's kind of saying the same thing. Sometimes we want to brake a motor, sometimes we want to accelerate a motor, so it depends on what stage we are in the motor application. And then something I want you to think about, if this is our equation, right? We start here as force times radius equals the torque. And in this particular case, 150 Newton meters, is developed when a force of 300 newtons is applied to a radius of 0.5. He says, what would happen if this radius changed and the radius was 2 meters now? Okay, so would the force that I needed to apply go up, or would it go down in that case? Well, let's see what would happen. All right, so the torque is 100 Newton meters, and here's the force that I'm wanting to find out. And now he's saying the torque is going from 0.5 meter to 2 meters. What would the force to stop this rotation, would it increase or would it decrease? Well, we know from just thinking through something like this, it's easier to stop a large rotating wheel than it is a small rotating wheel. And so the same thing applies here. And if I solve for force, I'm going to get 150 divided by 2. And so instead of having to apply 300 newtons to a radius of 0.5 meter, I would only have to apply 75 newtons to stop this 2 meter wheel from rotating. All right, I'll stop there. We'll pick this up, get ready for the next section.